Hello students, today we are starting a new question series. Actually, it's part of electronics essay question series. So we have done couple of electronics essay type questions. Actually, those questions are model paper questions and easy questions, actually small essay questions. But today onwards, we are planning to do past paper electronics questions. Students, I'm telling you this because electronics essay question is not that hard as you think it is, or it would be. It's mainly because you haven't practiced that type of questions. Sure, I'm telling you this, before the exam, at least couple of months before the exam, you have to finish your theories, then only you have time to practice. That is there, right? So even for matter and radiation, if you finish your theories at the last minute and you cannot practice matter and radiation questions as well, because I'm telling you this simply because electronic questions and matter radiation questions are easy, comparatively, relatively easy. So students, just try to go through with these questions, try these questions first and then go through with the explanation. And there'll be some of the questions I'm recommending you to do again. So practice that type of questions. I'm pretty sure you will learn something here for sure. So let's go to the question now. Students, now we are getting into 2024 electronics essay question. Actually, this question, it has 2 marks. Mainly it's from gates. Actually, mainly it's from gates, but still they are starting the question giving us a circuit diagram of transistors, and these transistors together act as a logic gate, right? So these type of questions, if you have practiced past paper questions in 2007, there's a question closer to you, and 2008 there's a question closer to this, and even in other years there are questions that are closer to this. But if you have done past papers, that's what I'm saying, if you have done past papers, students, this is quite similar to you, quite familiar to you, right? Similar type of questions. So let's dive into the question now. Let's start reading. Right, in the question, consider AND gate circuit made of considering transistor operating as switches as shown in figure 1. The circuit consists of 3 input NPN transistors, T1, T2 and T3, right? So this is T1, T2 and T3. In the beginning of the question, actually they are telling it's similar to an AND gate. They are both has to be equal for it to be 1. So, they are giving hints, right, when they give the question. Remember these things, right? While transistor T3 controls the final output X, the circuit operates VCC 5 volt. That's a supply volt. So you have done questions, you know VCC is a supply volt, 5 volt here, right? And crucial points, VBE is 0.7 volt silicon transistors, and of course beta. What's beta? IC over IB, that is 100, right? And then finally they are telling the maximum or the desired collector current for all, it is 4.8 milliamperes. 4.8 milliamperes, this is for this, right? And for the others, it's desired current for T1, T2, it's 4 milliamperes. For these, it's 4 milliamperes, right? Okay. So we have, these are the data that are available for us, right? Let's dive into very first question. Consider the situation when both input A and B are at 5 volt. Here input A, here input B, both are at 5 volt, right? Calculate the base current of T2 here, hence show that T2 is in saturation mode, right? Saturation mode, right? Saturation mode. Okay. So if this potential is 5 volt here, if this is 5 volt, obviously we can see that transistor is in active region, right? It works because here it's 0 voltage and VB is 0.7 volt. So the potential here, so here it's 0. Here it has to be 0.7 volt, and that's possible with this 5 volt. Right? So the rest of the potential, here is 5 volt, here it's 0.7 volt. So the difference across 10 kilo ohms will be 4.3 volt. They're asking us to prove that this T2 transistor operates in, yes, saturated region. Here the only saturated region, saturated region VC is a very small value. Likewise, there are certain things that you know, but here in the question they are giving us the value of IC. Desired IC is 4 milliamperes. Correct, right? Yeah, 4 milliamperes. And also beta is given here. Beta equals IC over IB. Here it's 0. IC 4 milliamperes. So IB will become, yes, 4 divided by 100, right? 0.004 milliamperes or 4 microamperes, right? Likewise. Right. Let's find the IB value here. If it's greater than this 4 milliampere, that's our answer, right? So what we should do, we know it's 4.3 milliamperes, that's across this 10 kilo ohms resistor. That's okay. Applying V equals IR for it. So it's 4.3 I, that's we are looking for IB. R value 10 into 10 to the power 3. So IB equals 4.3 divided by 10 into 10 to the power 3. I'll bring it up here. So it's 0.43 into 10 to the power minus 3. So 0.04 milliamperes, that's the required amount. Here it's 0.43 milliamperes, and that's much greater than the desired IB current. That's what you have to write. You have to calculate all this, and then you have to write the desired IB value. The IB value is much greater than desired IB value. So the transistor is in saturated region, right? That's what they're asking, right? So transistor is in saturated region, right? Calculate the base current T1, hence show that T1 is saturation mode, right? Now we know this transistor operates, so current flows downwards, and they have given in their data VC is 0.2 volt. So here this potential, it has to be 0.2 because it's operating. So I'll take point voltage here 0.2 as. Here I took the potential at 0. Right? It's connected to ground level. But here now it's working. So VCE, they are telling it's when in saturated region it has to be 0.2 volts. So I'm putting 0.2 here. Right? Then as the usual method I was doing earlier, so what we have to do, we need to find the potential here. Assuming the transistor in active region, forward bias, the potential difference VDE is 0.7. So the difference, it has to be 0.7. So the value here, it's gonna be 0.9 volt. Slightly different from this one. Right. Again, the very same method we apply here. We need to take the potential difference across this 10 kilo ohms. What's the potential difference? Here is 5, 0.9. So difference will be 4.1. Go back here. So it's 4.1 volt. So we are applying V equals IR for this 10 kilo ohms. 4.1 equals 10 into 10 to the power 3 into desired IB. So IB will be 4.1 divided by 10 into 10 to the power 3. So just like we did in the previous question, again we are getting the IB value is equal to 0.41 milliamperes, and it's much greater than the desired IB value. So we need to write that down, and then we write the transistor T1 also, that is in saturated region. So we have done first question 1 and 2 parts. Now moving into the second part. In this part they are asking us to consider the situation when neither A equals 5 and B equals 5. A equals 0, A equals 5, B equals 0, A equals 0, B equals 5. Right. State the operational state on and off of T1 and T2 for each, considering the current conduction from collector to emitter. No calculations are needed, right? No calculations are needed. Let's start with this. A equals 5 and B equals 0, right? So A equals 5 volt and B equals 0 volt, right? First thing what we have to do is, right now we know when this is 0, the transistor operates in cutoff region because there's no IB, so no current is allowed to pass through this transistor T2. So even if a current is possible through when it is 5, actually we know that the circuit will go through saturation mode, but still this current cannot pass through this circuit because this is in cutoff region, so no current can pass through this. So even if this is 5 volt, both transistors cannot operate in active region, off and off. That we have to tell, right? So we have to start from here. T2 transistor operates in cutoff region, so no current passes through it, no IC passes through it. Because of that, at T1 transistor, the collector current will not pass through T1 transistor. So that transistor is in cutoff region as well. So both of in situation. Like that you had right. In the second scenario, A equals 0, again the very same thing will happen. What we have to tell is A0, T1 transistor is in cutoff region, no IB, no IC. So since this is not operate, so there will be no current through even for T2 transistor. That's our second answer. So you have to write it properly and no calculations are needed. Right. Moving into third. Calculate the base current of T3 here. The base current of this IB here. Okay. Calculate the base current of T3 when either T1 or T2 is off. Hence, show T3 is saturation state. Right. When this is again, calculate the base current of T3 when either T1 or T2 is off. Either T1 or T2 is off. Hence, show T3 is saturation. Right. So now this transistor is in saturated region. Okay. One of these is off. That means both are in off, right? No current can be transferred through these. That of course we know, we have discussed that in previous question. So the potential, there won't be any current through this. So the potential here, it has to be 0, right? 0. Can it be? Yeah. So there will be no current through this path. No current. So the current can easily pass through this path. So we don't have to worry about this. So the potential here is 5 volt. So this is the path of the current. It goes to this path. So then the current IB, for T3 IB, we need to write the equation again. So let's write the equation. The potential difference for the here it's 0. For proper operation, VB is 0.7. So the potential here, just like we took it earlier, it's 0.7. So the potential difference across this 9 kilo ohms and this 1 kilo ohms, it comes together, right? See the path, it comes together. So the potential difference is 5 minus 0.7 equals IB into the total resistance 9 plus 1 in series. So it's 10 into 10 to the power 3. So we get IB equals 4.3 divided by 10 into 10 to the power 3. So just like we did earlier, and we have to do the very same method. IB equals So 0.43 milliamperes. So desired IB, it was 0. Again we have to write it, right? Beta. So IC is 4.8 milliamperes here now. IC, so IB, so it's 100 here. So IB equals 0.0048, right? Milliamperes. Here we get 0.43 milliamperes, much greater than the desired IB value. So T3 transistor in saturated region, that you have to run. Then you are proving T3 is in saturated state. Moving into fourth part. What are the values of output voltage Vx? Here Vx for the following input conditions, state the operating mode either on or off. T3 for each case. Case 1 A5 B5, right? A5 B5. So A5 B5 we know both works properly in saturated region. So the potential here, here it will be 0, here it will be 0.2, the difference we see again 0.4 here voltage. Right. I hope you understand that. Potential here is 0. VCE is 0.2, so the potential here is 0.2. The same potential here is 0.2. Again the difference again 0.2, so 0.4. Right. The required amount to pass through this BE junction, that is this 0.7, but the amount we have here, the potential, the point here potential is 0.4. So that is not forward bias. The potential is not enough. That means the transistor is in cutoff region, it's off. So this is basically off. If this is in saturated cutoff region, you know that no current, no IC passes through it. So potential here is 5. No current passes through it. So the potential here Vx, it has to be 5. Right. So it's 5 volt. You write that down. And the second part, A5 B0, whatever it is, we know that no current passes through it. No current passes through it. From the previous experience we know. Right. So we can write down A5 B0, transistors off. So there's no current through this. So current flows through T3 transistor. When that happens, T3 transistor in saturated region, we have proved it earlier. So T3 potential will be here 0. Saturated region, Vc as in Vx here will be 0.2 volt. In both cases, it's 0.2. Right. So we have finished fourth question. Now we are in part B. Right. Actually, it's the second. So it's again, it's from gates. Completely, it's from gate. Right. It's a gate question. Let's read the question now. Consider the block diagram shown in figure 2, a logic comparator, which compares two binary digits A1 and AB. The output F1 becomes 1 only if A1, B1 are same. Right, students? So while doing questions, actually you should have certain kind of understanding about logic gates. So here they are telling the F1 output becomes 1 only if A1 and B1 are the same. So when both are same, do we have in our logic gates anything like that? If you can remember something, XOR, when both inputs are similar, it gives 0 signal. So this is exactly opposite. So you should understand this opposite of XOR, right? Knowing that, write down the truth table for the comparator. Just write down what they are telling. Draw the truth table then. A, B. And what are the values? 0, 0, 1, 0, 0, 1 and 1. The output they are telling, when these two are equal, it's 1. When these two are equal, it's 1. Otherwise, it's 0. So when we do questions, we know how to construct an equation. So we write down this as A bar dot B bar, right? That's how we get this one. And again from this one we get A dot, simply A dot B, right? That's it. So what we have to do, we are at the end. So our logic expression, they're asking us to find that logic expression, the table and expression, yes. So F1 has to be A dot B bar plus A dot B. That's our answer, right? Then we are moving into the third one. Write down the logic expressions we have done using the above truth table. I've done it. And third one, write down the truth table of logic expression of XOR. So they are getting us closer to that XOR thing, right? If that automatically comes into your mind before reading that, that's great. Write down the truth table for logic expression for XOR. Right. Are we there? No, these are theories, right? So for XOR, we write A, B, and let's say output is F, A, B, B1, F1. Okay. 0, 0, 0, 1, 1, 0, and 1, 1. Right. Okay. And then what we have to write down, we know that when both inputs are equal for XOR, it gives 0 output. 0, here it's 1, here it's 1. So this is the truth table for it, you have to draw it. And they're asking us the expression for it. You should remember the expression F1 equals A plus B. That is the answer for third question, right? So the fourth part, we are moving into the fourth part. Draw the logic circuit of comparator using XOR gate and NOT gate. Right. So we have understood before that this is the F1 output is the exact opposite of this. So what we have to do is, so they are telling it's here 1 and here is 0 and 0. So exact opposite of this. So what we can do, so we get XOR here, right? And we connect it to NOR gate. A1, NOT gate, yeah, NOT gate. So we have to draw this and we get marks, right? Fifth one. Draw the logic circuit of the comparator using XOR gates. Okay, only XOR gates without using NOT gate. Hint, connect one input of XOR gate permanent to logic level 1 or 0. So they are giving us a hint. So we have to use it anyway. So XOR, we have to draw this anyway. So it's A or B. And the output comes like this. And it should be connected to another XOR because that's the only available gate we have now. Let's connect it to XOR. Right. So if this is 1 and 1, this 1 and 1, here we get 1. Right? For that, if this is 1 and 1, here we get 0, right? This is 1 and 1, here we get 0. But still, we need to get out 1, right? Outside. So we make it 1. Permanently 1. So when this is 0, 1, 1. 1, 1, 0. So it is happening. Right? We have answered. Question number 6. Using the block diagram, this one, an additional 3 input logic gates, draw circuit composite diagram for 3-bit comparator using A1, yes, all these values, right? Students, you just to understand these type of questions, actually you have to practice questions. So if you have practice question, 3 input AND gates questions you must have done. So if only you have done that type of question, that idea comes into your head. Otherwise, you will feel like you are stuck there. You don't know what to do with this type of question. Students, if you are facing a situation like this in electronic essay question, but you have to go with your gut feelings or whatever you know, just write it down. Don't think complex things because you cannot think new things. So just what you have to do is you have to write the things you know only, right? Remember that. Don't be that much of creative when you are doing questions. If you are trying to be too much innovative, you are going wrong. So if only you have done this type of questions, as in 3 input and gate questions, then now you would understand what to do, right? So basically what we have to do is we have to connect all these inputs, outputs to a single 3 input and gate. That's it. You draw that, you have the answer, right? That's what we have to do. So let's draw it. Right. So we get 3. Likewise here, this block A1, B1, we get the output, we connected to an AND gate. And we get another block A2, B2. That's also connected. And we get another one A3 and B3. That is also being connected. That's it. This is it. Right? No complex things and all, but only if you are familiar with it, then only you know. Right? It's connected to an good. Then they are telling in the question even connected to a gate. Actually, it's basic. And normally we connected to an. And we are in parts. Right? If you have done up to C, you should be good with logic gates. This is not that hard. Right, but still students, if you have done only past paper questions, you have this kind of experience, questions like this. So some questions you have assumed 0.2 as 0, in some questions 5 volt as 1, if you have done previous questions. So then only this is not different, it's quite familiar to you. So here in this question they are telling P and Q inputs. About P and Q inputs. So here, what they are doing, telling is logic level 1, for logic level 1, between 2 volt to 5 volt is logic level 1. So whatever the values it takes, the circuit will take it as 1. So logic level 0, it's in between 0 to 0.8. Alright, and whereas for Q, it's 3.5 volt to 5 volt, right? Yeah, 5 volt, and 0 to 1.5. There's a difference. And output of this will be 2.7 volt to 5 volt. Logic level 1 output. 2.7 volt to 5 volt logic level 1, and 0 to 0.4 logic level 0. 0 to 0.4 logic level 0, and for Q it's 4.95 volt to 5 volt, and again 0 to 0.05. Bit of a smaller value, right? Okay, let's get into the question. In one circuit, the output of P is connected to input of Q. Output of P, right? This is P. Output of P is connected to input of Q. So what are the output values of P? It can be 2.7 volt to 5 volt, or it can be 0 to 0.4. We wrote it well, right? Yeah. And now Q is looking at it, right? 5 is fine. Let's say 2.7 to 5 volt comes. 5 is fine, but still 3.5. So this one Q will recognize up to 3.5 as 1. So below 3.5, it will take it as 0. So this is giving it a logic level 1, but Q is taking it as logic level 0 in some case. Some case it might work, but basically we can assume it won't work, right? So they're asking, do you expect the circuit to operate properly? No. So logic level, there's a difference here. This is the logic level. This logic level difference, it won't help it. right? So it won't operate properly, right? Moving into students, now we are in the last part of the question. In another circuit, the output of Q, so now Q is here, it gives a value, it goes to P, right? Do you expect the circuit to operate properly? Briefly explain, right? Let's see. So output, let's say it's 4.95 volt to 5 volt. So this will take it as 2 volt to 5 volt, or is 5 to below any value. This one will, if this is 1, this one will also recognize it as 1. Yeah. Let's see the 0 value. It's between 0 to 0.05, and this one will recognize 0 to 0.4 volt as 0. So Q1, P take it as 1, Q0, P take it as 0. So logic levels are equal. This works properly for better operation. So this is the last part of the question, students. If you have gone up to this level, you have collected 15 marks. Maybe you haven't pointed out properly certain explanations, and you might miss 1 or 2 marks. Do not worry about it, students. I don't think we can get 15 out of 15. We might make small mistakes sometimes. But students, remember that. Get the marking schemes of the past paper questions and analyze them. When you are doing essay questions, you have to analyze the past papers, the way they have given the answers, right? Students, go through the marking schemes and then do questions. But when you are doing MCQ questions, students, you have to be good with it. You use shortcut methods, whatever it is. The method, it won't help that much. It will be faster, that's a different story, your method, but you don't have to be careful about writing down everything and all that. But here we have to write down proper answers, steps and all that. So to be familiar with the steps and all that, you should look at the marking schemes. Remember that, students. Go through the marking schemes, the way they have given the answers. You do the question first, then go through the marking scheme, see how many you can collect, right? Like what are the marks you can get, right? I hope, students, you have learned something from this question. So I am suggesting you to try. If you are planning to do essay question in electronics, you have, let's say you start from 2001, you have more than 20 questions, right? Essay questions with answers. So try them. And I'm pretty sure you will get good marks. All the best. Yes.